Jai Hind, welcome to class of Analog and Digital Communication. So we are going to talk about angle modulation today. This is the second lecture. So what is angle modulation? It is altering the angle of a high frequency carrier wave with respect to the instantaneous value of the message signal, right? If I talk about a simple sinusoid wave, it does have a simple sinusoid, xt equals to a sine omega t, a pure sinusoid, right? If I want to vary its characteristics, I am left with two options. Either I vary the amplitude or I do vary the angle portion, right? So varying the amplitude of the carrier wave with respect to instantaneous value of message signal is called amplitude modulation, and varying the angle is about angle modulation, right? So how do I represent the signal? If I want to represent my signal with whom I'll be doing some variations, let's suppose instead of xt, I do represent it with st. This is after modulation. So I do, this is about my carrier wave. We know that we represent my message signal by either MT. These are some standard notations that we give, right? And carrier usually by this. And modulated wave, I usually take notation which is ST. So after modulation, if I see here, the amplitude part will remain constant, and this amplitude will be the amplitude of my carrier wave. So I represent it with AC, and cos theta IT, this is the instantaneous angle of my wave, right? Angle of this angle consists of what things? Let's see. We know in amplitude modulation, amplitude is varied. In frequency and phase modulation, these are related, right? If I vary the angle of my wave, I'll be varying the angle. When I vary the angle of my wave, I'll be varying the frequency and phase both. So these two are related, because what is this angle? This consists of, if it is a pure sinusoid, this will be omega ct, and if there is some phase variation, that is represented by plus minus, you can say phi t, right? So this complete is the phase angle, and this is the phase variation. So when I vary the phase, the complete angle varies. When I vary the frequency, which is 2 pi f, when I vary the frequency, this is also going to affect the complete angle, right? So in angle modulation, we study about frequency modulation and phase modulation both, right? And in frequency modulation, amplitude and phase of the carrier wave remains constant. This can be better by observing the following. See, if this is the waveform for my baseband signal or my message or information signal, which is a low frequency signal, this is the amplitude of the signal, and this is here I represent the time axis, here the voltage axis, and this is the carrier wave. So how may I represent my my FM? I would rather draw message signal here to make it easily understandable, right? So here if I draw here my voltage reaches peak, here this is the minimum, Vmin, this is the max. So when this amplitude or voltage increases, the frequency of my carrier gradually increases. It reaches the maximum value when the amplitude of my message signal is maximum, and it reaches the minimum value when the amplitude of my message signal is minimum. So considering my information or message signal as a voltage signal, the frequency of the carrier is varied with respect to it. So this is about my frequency modulation. This has variable frequency, whereas the amplitude is kept constant, right? Equation: instantaneous frequency can be represented by carrier frequency plus some variation in the message, which is a factor of this frequency sensitivity, right? This can be hertz per volt, because how much variation in the frequency with respect to my message signal, which I consider as a voltage signal, right? Now if I talk about what are the various types of FM, we have narrowband and wideband FM. Depending on the index, which we have discussed already in the previous lecture, beta, which is given by this, beta represents my modulation index, which is the ratio of maximum frequency deviation, that is how much frequency varies from the central frequency. Like this is my central frequency, and this is the maximum frequency it achieves, and this is the minimum frequency it achieves. So how much does it deviates from the central frequency? Like if fc and this is the f max it reaches, and in this direction f min. So this difference is my del f, right? And fm is my message signal frequency, modulating frequency, right? So depending on the value of beta, if it is it is calculated in radians, this is an angular thing we are talking about. So if this has a smaller value, we call it a narrowband fm, and it is larger. So now what is the reference for it for comparison? What's larger, what's smaller? We compare it in radians, and we consider if beta is less than 1, we consider it to be a narrowband FM, and when beta is greater than 1, we consider it to be a wideband FM, right? So here are some certain examples which I wanted to quote here. Like it is narrowband FMs, these are usually used for the applications like mobile communications, police, wireless, ambulances, etc. And if I talk about wideband, then these are used in FM radio, TV, right? It has a wider spectrum. If I talk about the bandwidth of narrowband FM, it has bandwidth quite similar to amplitude modulation, which it consists of the bandwidth of narrowband FM would be 2 FM. Like this will be consisting of FC and FC plus FM and FC minus FM. There will be in the spectrum, it will have 3 frequencies, right? So the bandwidth would be twice of FM, which is quite similar to AM. But actually the FM that is actual FM, that is your wideband FM, it has infinite bandwidth. Bandwidth expands to infinite. Although communicating using infinite bandwidth sounds somewhat impractical. So we have a rule for it. Carson rule, which we discussed in the previous lecture. As per that, will limit the infinite bandwidth into some measurable amount, where your bandwidth is given by I would rather term it as transmission bandwidth, which is equals to twice of del f plus twice of fm. This is the transmission bandwidth of fm, right? This is the transmission bandwidth of fm. So we limit it to some value where amplitude is visible or has some impact, right? Because when the bandwidth expands from minus infinite to plus infinite, the frequency spectrum, if we check the frequency spectrum, the amplitude values keep on diminishing. This we have already discussed in while we have explained Carson's rule. Now next thing we talk about is how do we generate FM. So there are different ways of generating FM. Like we discussed, there are 2 types of FM, narrowband and wideband FM, how to generate it. If I specifically talk about generation of narrowband FM, we know that the standard expression for FM can be written as S equals to AC cos 2 pi FCT plus 2 pi KF MT dt. What does it mean? Here AC is my carrier amplitude and FC is my carrier frequency. Here KF defines my frequency sensitivity. This is the integration of the message signal, right? This we have discussed while we have related FM with PM, right? The complete if I vary the frequency, how is it going to affect the complete angle? That can be demonstrated by taking integration of my message signal. This is what we have discussed already. So this is how I can represent my modulated signal for my FM, right? Here my ST is if I expand it, I do get this, right? So for narrowband FM, I have to take care of one thing, that my modulation index must be less than 1, right? How? We know that for smaller angles of cos, as cos theta, for smaller there is little correction here, for smaller angles of sin theta it should be 0, and for smaller values of cos theta it is approximately close to 1, as cos 0 is 1 and sin 0 is 0, right? So by using the above relations, we'll get narrowband equation as if I put the value keeping beta and keeping the modulation index smaller, I'll replace sin theta equals to 0 and cos theta equals to 1. and I will deduce this expression as this, st equals to AC cos 2 pi fct. This cos term I have written as 1, and this sine term I have removed, right? So this is how I get the expression for narrowband FM, right? So how do I generate it? For generation of narrowband FM, I can use such kind of configuration, right? As from the expression I could see that message is not directly provided, messages first pass through an integrator. So I'll be using an integrator to which I give input, which is my message signal. Next, let's check the expression that has to be multiplied with my carrier, but I have to see whether it is cos or sine. So what do I do? To the product modulator, one of the input is integration of message, whereas if my carrier was a sine wave and I get to see here it is getting multiplied with cos wave, then I have to provide a minus 90 degree phase shifting to this, right? So to the product modulator, one of the input is my integrator input, another is my phase shifted value of my carrier wave, right? Then I have to add another factor, which is 2 pi kf, which is collaborated here, and the summation of these two, and this goes in feedback as well, right? So what do I get here is my narrowband FM. So one of the input I get here is message integration multiplied by the cos wave, and this factor is added, and plus addition of the cos wave. We can see it from here, right? If I expand it, I'll get AC cos 2 pi fct plus AC cos 2 pi kf integration of mt dt. So this portion AC cos 2 pi k integration of mt dt, I am going to get it from here, and this portion AC cos 2 pi fct, I am going to get it from here. So when these are added, I do get the narrowband frequency modulated waveform, right? This is how I may generate NBFM. Here the integrator is used to integrate the modulating signal MT. True, the carrier signal is the phase shifted by minus 90 degree to get AC sine 2 pi fct with the help of minus 90 degree phase shifter. The product modulator has two inputs, this and this. True, it produces an output by which product of these two inputs. True, this is further multiplied with 2 pi kf by placing as a block. Done. In the forward path, the summer block has two inputs, which are nothing but two terms of narrowband equation. Okay, we already discussed it, right? Now, if I talk about generation of wideband FM, if I have to generate wideband FM, there are two ways of generating it. Either I use a voltage control oscillator, and that method is called as direct method, or I generate indirect method, which is also called as Armstrong method. Let's see. In direct method, what do I do? With the help of VCO, voltage control oscillator, as I know, when my input signal is this, carrier is this, the output I get is some variable frequency that depends on the input voltage. So governing oscillator should be a voltage control oscillator. The oscillator which is generating this must be governed by this. So I do simply use a voltage controlled oscillator for generation of this kind of FM, right? So we usually use a Hartley oscillator for it that has high quality factor, right? So we may use that, and we can generate wideband FM. Here the modulating signal is applied as input of the VCO. VCO produces an output which is nothing but wideband FM. I know that instantaneous frequency depends on message. Instantaneous frequency is carrier frequency plus message multiplied by my frequency sensitivity. Here Fi is the instantaneous frequency of the wideband FM. True. Now let's talk about the indirect method. If I talk about indirect method, this is also called as Armstrong method. Here what do? We generate narrowband FM first, and we know that for narrowband FM value of beta is small. So with the help of a product modulator or a multiplier, not product modulator, sorry, with the help of a multiplier I can increase the value of beta. Usually what we do, we increase the deviation, and we know that beta is directly proportional to del F. When with the help of a frequency multiplier, if I'm able to increase del f, I'm able to increase the value of beta, and from then I can generate wideband FM from narrowband FM. So this is called as indirect method of generations. So we do use multipliers, frequency multipliers. Let's see. I give input, which is my modulating signal, to a narrowband modulator, and this narrowband we just discussed, this we can generate, and it requires a carrier, which is true. After this, I pass it through several frequency multipliers until and unless I get the desired value of del f and corresponding to it desired value of beta. So I am able to generate wideband FM, right? So this is my direct method of generation, which is also called as Armstrong method. Here this block diagram contains mainly two stages. In the first stage, the narrowband FM wave will be generated using NBFM modulator, narrowband FM modulator. We have seen the block diagram of NBFM modulator at the beginning of this chapter. We know that the modulation index of this is less than 1, true, beta less than 1. Hence, in order to get the required modulation index greater than 1 of FM wave, we choose the frequency multiplier's value properly. Now I have to increase the value from less than 1 to greater than 1. So I have to choose frequency multipliers accordingly, right? So now let's talk about what are my frequency multipliers. Frequency multiplier is a nonlinear device which produces an output signal whose frequency is n times the input signal frequency, where n is the multiplication factor, right? Isn't it true? So frequency multipliers play an essential role in generating my in increasing the value of del f, or in corresponding to it increasing the value of beta, and finally we get to generate my wideband FM, right? So let's go through what we have discussed today. As this is the second lecture of angle modulation, we again gone through the brief of what is angle modulation, the expression for it, how angle modulation consists of frequency and phase modulation both, because if I vary the frequency or the phase angle, or if there is some phase deviation, it is going to affect the complete angle. So we study FM and PM under angle modulation, right? And this is how I may draw the waveform for my frequency modulated wave. The frequency of carrier will vary with the message signal. As it is rising, frequency will increase. As it is falling, frequency will decrease. This is what we have discussed. We discussed about the frequency sensitivity, which is hertz per volt. Then we discussed about two types of FM, which is narrowband and wideband FM, depending on the value of beta. If beta less than 1, we call it narrowband FM. Beta greater than 1, we call it wideband FM. And how do I calculate beta? Del f by FM, which we have previously discussed. Right? Now, generation techniques of narrowband and wideband FM. For narrowband FM, we do need a product modulator, a phase shifter, and a summer circuit. Right? How have we calculated? By checking the input, by checking the waveform for narrowband FM. What is the waveform? So we have seen it. Then block diagram, and after that, if we talk about wideband FM, direct method is using VCU, and direct method, which is also called as Armstrong method. If this voltage regulates the generation of frequency, I will be able to generate a wideband FM. And if I am doing it through indirect method, that means I am generating narrowband frequency modulated wave first. Then with the help of frequency multipliers, I am increasing the del f and in corresponding increasing the beta, and I am able to generate wideband FM, right? That's it for today, and these are the references that I have used. Thank you.